on log functions. Okay, lesson 3.2 is on log functions. So here's our typical log function. Y is equal to log base A of x. And these conditions apply. X has to be greater than 0. A has to be greater than 0. And A can't be equal to 1. Well, we can rewrite log functions as an exponential function because they are inverses of each other. So y is equal to log base A of x can be rewritten as an exponential function, and that would be x equals a to the y power. So let's take an example. Let's say 4 cubed is equal to 64. That's an exponential. And we want to rewrite it as a log function. And we can just say that the log base 4 of 64 equals 3. So this is how we go back and forth from log functions to exponential functions. And every exponential function has an inverse. And so log functions and exponential functions are inverses of each other. Let's take another example. 10 squared equals 100. That's the exponential function. We can rewrite it as a log function. We just say log base 10 of 100 equals 2. But if it's a base 10, like this is, we just don't write it, because if you just write log of 100 equals 2, this is assumed. If you don't put the base in there on a common log, it's assumed to be base 10. Okay, let's look at a few more examples. So find f of x equals log base 4 of x for x equals 16. So we're going to rewrite it log base 4 of 16. That means that 16 equals 4 to the y. And 16 is 4 squared, so y equals 2. Let's look at the next one. Find f of x equals log base 2 of x for x equals 64. So we write log base 2 of 64, rewrite it into an exponential. 64 is equal to 2 to the y. And so this is going to be y equals 6. 2 to the 6th is 64. Okay, next one. Find f of x for log base 5 of x for x equals 1. So we're going to write log base 5 of 1. And that converts to 1 equals 5 to the y. So y is equal to 0, because anything to the 0 power is going to be 1. Okay, let's look at some common logs. These are all common logs because they're base 10. So log of 1 is 0. That's because 10 to the 0 equals 1. Log 10 equals 1 because 10 to the 1 equals 10. And log 100 equals 2 because 10 to the 2, or second power, equals 100. And then log 1000 equals 3 because 10 cubed equals 1000. So this is kind of one way to remember how to go back switch from logs to exponentials. Now some more examples you can do on your calculator. So log of 1/5 is equal to negative 0.699, or you could say 10 to the negative 0.699 is equal to 1/5. Or you could have the log of 3.25 is equal to 0.512. Writing it as an exponential, 10 to the 0.512 is equal to 3.25. Now, what if you were to take the log of negative 4? you get error because you can't take the log of a negative number. You're not allowed. You go to algebra jail if you try to do that. So let's look at some helpful log properties. A couple of them we've already talked about. First one, log base A of 1 is equal to 0. The other one we talked about is log base A of A is equal to 1, and that's because A to the 1 is just equal to A. And so another one that comes in handy, write log base A of A to the x. That's just equal to x. Or we could write, put it in the exponential, we would say A to the log base A of x is equal to x, because these are inverses of each other. So these two functions or equations come in pretty handy when solving log problems. So another one that comes in handy is the one-to-one principle. So if log base A of x is equal to log base A of y, then x equals y. And this is the one-to-one principle. Okay, the book has more log properties, and also the handout, the Math Bits handout has more log properties, but let's just do some more examples. So let's say log base 5 of 1, well, that's going to be equal to 0. Well, let's say log base pi of pi, well, that's going to be equal to 1. If we had 7 to the log base 7 of 9, that's going to be equal to 9. If we had log base 6 of x equals log base 6 of 3, then that means we're solving for x using the one-to-one. Since these bases are the same, they're both base 6, they have to be the same, so then that means x is equal to 3. Okay, let's do another one. Log of 4 minus 3x is equal to log of x plus 2. Well, these are both the same base. They're both base 10. And so we can just say, well, 4 minus 3x is equal to x plus 2. Do the math on that, and we have x equals 1/2. Okay, so let's take a look at a graph of the exponential function, f of x equals 2 to the x, and its inverse, g of x, which is equal to log base 2 of x. So let's do a xy table, look at some points to plot. First going to plot f of x equals 2 to the x. Okay, so when x is 0, y is 1. When x is 1, 2 to the 1 is 2. When x is 2, 2 squared is 4. Let's get one on the other side of the y-axis. When x is negative 1, 2 to the negative 1 is 1 over 2, so it's 1/2. Let's plot those. So here's negative 1, 1/2. Here's 0, 1, 1, 2, and 2, 4. So this is our typical exponential curve. Now let's plot g of x. So let's do our xy. So in this case, the y is g of x. So when we can't take the log of 0, that's not allowed. So when we take log base 2 of 1, y is 0. Log base 2 of 2 is 1. Log base 2 of 4 is 2. And log base 2 of 1/2 is -1. And you notice between these two tables, XY tables, their Y values and X values are reversed. And we know that's what's going to happen with inverses. So let's plot them. 1, 0, 2, 1, 4, 2, and 1/2 -1. And so this log curve is going to do this. And also, since they're inverses, you know that they are mirror images in the y equals x axis. So we could draw a dashed line here. This is y equals x, and they are mirror images. So this proves that f of x is an inverse of g of x. Now for natural logs, we write a natural log as ln, and natural logs are base e, just like a common log is a base 10. Well, you don't have to write the e as the base, just like you don't have to write the 10 as the base for a common log. Thing is, natural logs are used a lot more than common logs. So it seems like the natural log would be called the common log, but it's not. So ln is a natural log, and the same log properties apply to natural logs as common logs. So just for example, let's say f of x is equal to natural log of 73.25. You just take the log of 73.25 and you get 4.29. Also, we could do another example. Let's say f of x is equal to log of 2 plus square root of 3. We just add 2 and the square root of 3, take the log, gives you a 1.317. So natural logs have the same properties as common logs, but you'll find that we'll be using natural logs a lot more often than common logs. Okay, so that's it for 3.2.